Hi, good morning, and welcome to the ZP Developer Zone. So we do this webinar at 8 a.m. London time every Thursday, and I will jump into it because there's a lot, and it might easily go over the half an hour today. So we do have the ZP Academy. If you've got any sort of want free, let's say, education around some of the topics we discussed, then go to the ZP Academy. We do have these webinars, for example. We do this every Thursday London time. We do have collaborations. These are strictly speaking with, I would say, collaborations when they're free or with academia, things like Horizon 2020. We do post jobs. We do have the developer zone, and we do have workshops. So my next slide, I'll just kind of say that a lot of the questions that have come up this week are around topics like CGM. Also, there's pH in there as well. So we do have a lot of workshops running in 2023. For example, in January, we're holding a workshop that's just 100% online because we realize not everyone can get to these workshops, but I think the in-person workshops are the best, and we are holding them, as at the moment there's February, March, September, and October, various workshops. And so if your questions are around continuous glucose monitoring or pH monitoring or IVD development, then I would say please come to those workshops. Got a lot of questions today. So question number one is about developing an IVD. And question number two is about cell culture monitoring and bioreactors. Question number three is about cortisol sensors. Question number four is data from a glucose sensor. So I will dive into that quite deeply. Question number five is just about ammonium sensors. Question number seven was about making arrays of electrodes. Number seven was just a short one about sensor fabrication. How much volume does it take to make a sensor? Number eight is slightly unusual. It's about a fuel cell application or a larger scale application rather than just biosensing. Number eight was about, or number nine rather, was about hypervalue electrodes in a well configuration. Number 10 was about CBD. Number 11 is a CGM discussion, a continuous glucose monitoring discussion. I just want to say thank you for the comments online. I'm just going to take a quick look. Thank you, Prakiha. It's appreciated. So nice to see you this morning. Number 12 is about IVD meters and electrodes. And number 13 is about sensors with Bluetooth modules. So I will jump into it a little bit. I want to say quicker now. Question number one, developing an IVD sensor. So somebody wants to use a carbon electrode using some oligonucleotide recognition probes, which is a sort of another word for aptamers often. I mean, at ZP, we do this quite routinely. I will talk today about cartridge design and rapid prototyping. We have several ways of making a cartridge, including 3D printing. These are the sensors in a 3D printed cartridge here, so that does help with rapid prototyping. Instrument components. If people today are trying to do a they're trying to do a product where there's several assays running in parallel. We do actually have a platform for that. Now this person wants to actually run, let's say, 8 working electrodes, and we do have a technology for that. But I do want to talk about that a little bit. When you're doing parallel assays, do you have all the sensors essentially undivided? They're all just sort of able to be in the same drop, or do you actually divide the sample and do essentially 8 individual assays? And I will touch upon that. This individual is also interested in getting asked to consult on the assay, which is what we kind of do. So I've done these slides in the past, but we both functionalize carbon electrodes and gold electrodes. And we've actually put some work up of recent about our use of aptamers on gold electrodes. So if you're ever interested in at least just getting a sight of what this kind of data might look like, then just Google gold electrodes, aptamers, Zimmer Peacock, and hopefully you'll find it. And we have been using gold electrodes and these functionalizing gold electrodes for quite a while and making them into biosensors using antibodies. There's something. So I've put. This is just my own, let's say, memory to actually put any links you see today, I'll put them underneath the video. So if people want to make biosensors on carbon electrodes, that is really quite straightforward. We'll always talk about our Hypervalue carbon electrode. I also want to give the sense that actually we have a bit of a platform now, so that you can take one sample, divide it 6 ways, and actually do 6 assays on that. And that's not something you have to build from the ground up anymore. It's something that we have been developing. So I do have lots of videos about, you know, how we would go about functioning a carbon electrode. And it's important to say that obviously every time we function a carbon electrode, you know, we do a quick bit of cyclic voltammetry to make sure that that electrode did get functionalized. You know, so we're kind of following the process. It's probably also worth saying that, you know, I go into these slides in a lot more depth at one of our workshops as well. And then we test, you know, these kind of electrodes. You know, we add the analyte of interest, and the signal changes accordingly. You know, we get ourselves a calibration curve, and that's also something I do actually cover a lot in the workshops. And we can generally do what I call a proof of principle in about 111 hours. You know, so we can get people good data. There's actually 3 data points through. Some of these look like 2s and 1s, but they're actually 3 data sets. Sometimes we just get it so, let's say, precise that it looks like 1 data point. It's actually 3 data points in there. So we can do most IVD proof of principle in about 111 hours. And then of recent, I've been getting the team to really get into, I mean, we've always had 3D printing, but we haven't been 3D printing microfluidics as much. But actually that is something I'm really making that happen, because it is a good technique. You've got a lot of very good engineers these days, you know, and we've got so many 3D printers that, you know, we can actually produce quite a few, you know, let's say cartridges at a time. Now, if people come to us and say, look, I really want to do multiple analytes in parallel, you know, we actually can do it in the way I'm showing at the moment. This is a credit card format. Historically, I've always kind of pushed the credit card format, but as we explore the 3D printing, I don't think I have a preference. I think they both have different features and therefore benefits, but we do, you know, do the credit card format as well. And this was an early concept of a device that's now sort of come about, where we would be able to take something that was quite handheld, put it into a sample, wick up one sample and divide it in lots of ways. And that sounds something that we've actually, you know, bring into sort of as a standard product, not for us, but so other people can actually use it in their developments. The reason I've brought up the 3D printed cartridges today is some workflows are not quite so straightforward. In fact, if I sort of show that video again, this workflow assumes a very simplistic microfluidic, where you put the sort of microfluidic in the sample, and the sample is wicks up, it goes straight into the sensor, onto the sensor, and we just analyze it directly. That's the way we try to build things. Life is not always quite so, you know, straightforward. Sometimes you need to do processes like filtration. For some reason, you need to filter the blood. Sometimes you need to do lysis. You need to sort of break up the cells. I just want to say a good morning to Aftab as well. Aftab, nice to see you this morning. So sometimes the processes are a bit more complicated with lysis, then capture, and then separation. And I quite like the idea of magnetic, well, not the idea, this is something we've done, is magnetic beads for separation. Separation actually can be done in a couple of ways. It can be done by magnetic beads. It can also be done by, essentially, filtration is also a separation technique as well. So at ZP, it's not something I've talked about, at least for a couple of years in our, let's say, these weekly webinars. But we do have quite a lot of experience in making, essentially, magnetic pieces that work with our biosensors. And so we can do magnetic separation. I bring all this up because, you know, people inquire to us about IVD development, you know, rapid prototyping. So, you know, I think the big change today is we are actually getting, you know, we are starting to do a lot more microfluidic 3D printing, or 3D printing of microfluidics. And then also the idea of actually bringing a magnet into that assay and doing something like a separation using a magnet is really of no issue. In fact, I think in the middle video here, we've got a suspension of magnetic particles, and we bring a magnet to it. That's a pretty powerful magnet when I look at it, and, you know, we get a sort of, you know, very powerful magnet, and we get a rapid separation. So I do like magnetic beads. It's not something that we've talked a lot about, but it is something that we do have a lot of experience with. The particular inquirer is interested in a voltammetric assay technique, in particular square wave, but of course, you've got square wave, differential pulse voltammetry, not cyclic voltammetry. I don't think cyclic voltammetry is necessarily a good analytical technique, but I do want to say all of those are covered in our workshop, so come online to that workshop. And it's also worth saying that don't think that these techniques are excluded from you if you're doing if you're doing IVD or wearable sensors. This is our most recent wearables board. It can do everything. It could do, everything's a big statement, but EIS, voltammetry, amperometry, potentiometry, the world has really moved on. In this particular inquirer, I think they're actually quite interested in using several working electrodes in the same sample. So we do have that technology. I've put myself a little note here to say in silicone finite element modeling. It's basically just a way of saying, I think if we were to do something like that, sometimes we have to kind of actually, it's probably worth us doing a model of the different assays, and actually modeling it to see if the assays will do a crosstalk or what will happen. So the easiest way of doing it is actually just to have sensors that are further apart, or in this case, sensors that are literally in different wells, so there is no crosstalk. So before you dive in too much on putting lots of sensors in one sample, I think at the ZP approach these days, we can do it just as quickly as we can model it, but I think it would be worth modeling. Make sure that a glucose sensor isn't cross-talking with a lactate sensor, which, by the way, it probably would. So that's just, I sort of know the answer to it, but the model will kind of illustrate why that is actually happening. And we do get a lot of inquiries. People are interested in using our sensors in bioreactors. It's probably worth saying that all of our sensors are intrinsically continuous sensors. So the way we formulate these sensors, the way we formulate the glucose sensor, the lactate sensor, the oxygen sensor, the pH sensor, the conductivity sensor, they are intrinsically continuous sensors. And actually, I have some client data today which will kind of illustrate that, but they are intrinsically continuous sensors. We are already putting these sensors into bioreactors. We're working with universities and dealing with things like stem cells used in therapeutics, but also stem cells used in food production as well. And I want to say that the way we're dealing with this is bioreactors do come in lots of configurations. You've got little tanks or little stirrers. Bioreactors in a more sort of stirred batch reactor. You also got these kind of bag type bioreactors. So our sensors can actually go into these formats, and we do have the electronics and the connectivity, and we're able to send all that data to the cloud. So we have a really nice solution. But the variability in bioreactors and applications just throws up so many questions. We end up having to do this as what we call a product as a service. So rather than having an off-the-shelf product on this, we do actually have to run it as a service, because there's just so many configurations and demands and cell types that you can't just have one fits all. So we have to run it as a sort of essentially as a service. Question number 3, the questioner, this is a hard question for us, that the person wants to sort of know about our cortisol sensor and have a cortisol sensor. I won't ignore questions, even a tough question like this. And the reason this is a tough question is because we have some agreements in place that mean that our sensors can't be given out for free. So I apologize for that. So I want to acknowledge your question, and I want to say to you, that I want you to continue with your work and your studies, but this cortisol sensor is not something I can give out to you. What I can tell you is this is a electrochemical sensor. It's enzyme based. We're using a technique called amperometry, and it's really a repurposing of a glucose strip. So at Walgreens and CVS, which are pharmacies in the US, you can buy glucose strips. Those are designed to just discretely measure the blood glucose, once off. But we use that manufacturing technique, but we actually make a cortisol sensor from it. So we change the enzyme, for example, and it's also designed to be continuous use, and you can see that here. So I apologize that we're not able to send them free. There is some restrictions on us for that. and we can only sort of sell them or put them into projects. So I apologize for that. But I do wish you very good luck. You know, we were all at high school, so I do want to sort of applaud you and, you know, reaching out to us. So thank you so much. On question number 4, this is a long question. I need more water, but here it goes. All right, so this collaborator has an easy flex and a glucose sensor. They take the sensor from the fridge, they connect to the PCB, they wait for the sensor to stabilize, they dispense with a drop of solution, they record the response for 100 seconds, they remove the sample from the sensor, they rinse with DI water, let it air dry, and they repeat the steps. Now this person is actually trying to do a CGM sensor, so it's probably not the way to actually use and calibrate this sensor is the first thing. You know, removing the sample, DI water, let it dry. Every time you use a sensor, a glucose sensor, it can pick up history effects. So you're basically testing, picking up a history effect, testing, picking up a history effect, testing, picking up a history effect. You know, when you look at Dexcom, Medtronic, and Abbott, you know, their sensors go into that liquid and they stay there. They are staying there. They're not coming out and going back in again. They're staying there. So that's the first thing to note, that I have no problems with it, and your data actually makes a lot of sense, but it makes a lot of sense in the way that you're actually testing that sensor. This is a famous, this is, I make a laugh because this is one of our engineers called Andre. Andre's obviously still with us, you know, he's been with us for years. A lot of our early videos involve Andre and filmed with a video, filmed with a phone. But on Andre, in this video, and again, I'll try and put the link underneath the video. In this video, he shows you how to actually test a glucose sensor. First of all, he's waiting like 100 seconds to get baseline. And then he's pipetting in. He's got the sensor in a beaker. He's got the sensor in a beaker and the beaker's being stirred. That's the first thing to note. And then he pipettes in a concentration of glucose and the signal steps up. This is how we test CGM sensors. If you want to see this and do this with us, come to one of our workshops. You absolutely will do this experiment. You both make the sensor and do this experiment at one of our workshops. So he's waiting for it to plateau. He's going to pipette in another glucose solution in a minute. He's probably look here. He's waiting quite some seconds, like 40 seconds, and then he pipettes in again, and the signal jumps up again. So you can see, you know, he's being quite. We follow this procedure quite a bit. You know, if you come to us and you're on a CGM program with us and we're trying to determine, you know, the sensitivity or the calibration factors for that CGM, you know, continuous glucose monitoring system, then this is the way we do it. He even goes for a third edition here. This is the way you should really be essentially running those experiments. But your data still makes sense, by the way. I also want to say as well that if you want to do CGM development, you have to Google BioLink, and you have to Google the term BioLink and money raised. And you do, and I know people know this, but you do have to realize that BioLink raised $100 million to do glucose detection. Dexcom and Abbott have spent well over that kind of money to do this. So you can do proof of concepts, you know, using, say, materials off the ZP website. But ZP, when we're really doing this kind of glucose development with people, these are big programs, and you know, I sort of want everyone to kind of understand that, you know, you have to really jump in on this stuff, and it has to be well funded. But you know, there he's just actually, you hear Andre's just using a potentiostat that you know, one of our potentiostats, or one of the potentiostats I should say that we sell, and he's just using one of our glucose sensors. So you can do a proof of concept. And I'm involved in there as well. So let's look at the data as well. So the way they do this is they put a sample on there, they run the sensor. So for example, they run the sensor for 100 seconds. First thing they notice that it's 100 seconds. So in that video just now, you saw that Andre actually ran that for 100 seconds before he even started. But as I can see it, your sensor's already plateaued. So your sensor's plateaued, in this case, about 50 seconds. So you get your 100 millimolar signal, you take the sample off, you rinse the sensor, you dry it, you add on the 4 millimolar, 6, 8, 12, 14, and 16. So basically, it fundamentally works. And that's sensor 1, test 1, so I get it. Now, when you do the same sensor again, same sequence of events. It's not the sequence of events that we would do. We would, literally do the staircase. We kind of call it the staircase experiment, but you still get good results. But of course, they're not identical to the first results. And that really shocks people. But this is the reality of CGM, whether you're talking to, or whether you're looking at Abbott sensor, Dexcom sensor, Medtronic sensor, especially if you're sort of doing, laboratory one-off experiments like this, especially when you're learning your craft, let's say. I can see that they're actually plateaued off better off there. But I mean, you do have a signal versus concentration. That's that's proof of concept. This one, I can see there was a bit of a, in fact, it's not behaving itself. But I think it's behaving itself a little better later on, let's say. But again, you didn't wait the 100 seconds. No criticism. It's just, a reflection on the data. Sensor 2, test 1. No, I ignored this. I could see you had a bit of a, some of these signals were really sort of mixed up and messed up. But you can see something goes on here. What is this? So no big issues. But sensor 2, test 2. If you look at 50 seconds, actually, this time round, I actually reckon you should be looking at 100 seconds. I know that's a shift in time, but 100, 4, 6, 8, they all made, I think, approximately, they all made quite good sense. I think your best test was sensor 3, it was test 3, sensor 2, test 3, made some really quite good sense. So, well done, I would say. I just want to comment on something. You have quite a big signal jump between 0 and 4. This is really pertinency, because this person actually, in one of their questions, says, I want to monitor in sweat, and I think my sweat signals between 0 and 0.2. Test the sensors in the clinical range that's relevant. Don't test them in a clinical range that's not relevant. You're just gathering interesting data. It's good to maybe, do some tests, get yourself, wetted with, and familiar with the, with the technology, let's say, but test the sensors in the clinical range that you're actually expecting to do. Now they're doing some stability testing. So they dispense a drop on the sensor. They record for 1 hour. They remove the sample, and I think they do it again. So they put a drop on and they get a drift. This is at 0 millimolar. The drift is not terrible at 0 millimolar. Probably the reason the drift is not terrible is not really detecting any glucose. But I'll describe why this is happening in a minute. This one, you've got a drift up at 4 millimolar. This one's quite good, actually, because you actually go to 1,000 before you really kind of get this drift upwards. This one's, and then it starts really sort of drifting upwards. So yeah, they all have drift in them. So the question is I put a drop on there of glucose solution. I leave it there for about an hour. This one, you obviously have a sort of strange break in, and then it's really quite stable, actually. That one stabilized and then went up again. Why is this happening? I think it's because this is not, if we were doing stability testing, this is not what we would do. We wouldn't put a drop on there. Drops are a sort of, they're not necessarily stable. I don't want to the temperature I know the temperature in the room is probably fairly constant, but this is, a drop is not a large volume of glucose reservoir. The way we would test this is actually to put the sensor in a beaker if we were doing stability testing, and we would have constant stirring on. I think, again, that actually this person's best thing they could do is come to one of our workshops and actually do that experiment with us. So we wouldn't do it. We wouldn't do the experiment by doing a drop test like that. We'd actually do the experiment by putting the sensor in a beaker, putting a magnetic stirrer in that, and actually stirring it. Sometimes we turn the stirrer off when actually taking the recording, because stirrers can introduce a lot of noise. But the reason we stir is to sort of allow homogeneity. Otherwise, you have convective events going on in there, and the solution's not necessarily as homogeneous as we'd like. So we do actually tend to... that video I put to Andre earlier on is probably the one worth watching. The errors that they're getting, I don't think they're really getting errors, but the data they're getting is a function of the way they're doing the experiments. They do ask here, is it okay to take the sensor out of the fridge and just test it? It probably is, because the sensor is actually quite a small thermal mass, and therefore it probably warms up quite quickly. But do remember that enzymes won't work at 5 and 10 degrees very well, so it's probably good to have the enzyme at room temperature by the time you use it. The graphs are as expected, but the graphs are a reflection of the way you do the experiment. Um, when they do repeats, they get different results. They do. I mean, sensors, the way sensors are made in a very anhydrous state. So the first time that they see glucose is often when you test them. So then they get hydrated. So often there's a big difference between the first test and the second test, and that difference kind of goes down on the second, third, and fourth. If you look at the history of glucose monitors, what you find is they put a glucose sensor into a human body. They used to, the first 24 hours was actually really quite bad data. These days they wait 1 hour before giving you data. So they're allowing the sensor to swell and equilibrate. So look at real world CGM sensors, Abbott Dexcom Medtronic, you'll see that they actually wait something like 1 hour before actually giving you any results. He's having problems doing his model and calibration curve. Do the calibration curve in the way that Andre does it. The drift is more than I would expect. It is much more than I expect. I suspect you're doing a droplet. And this is really interesting that actually you're expecting concentrations in this range. You need to be clinically testing in that range. I think our glucose, by the way, I know our glucose sensors will work in that range. Not sure about those electronics. We've never done it in those electronics. In fact, later on, I'll be talking about some electronics that are a lot more, have probably you might have a bit too much noise. Don't think we've ever used them in that range, so it's a good point actually. But we have done analytes in sweat. Here's a link to a video where we've done lactate in sweat. I realize that we're only halfway through the questions. We're only we're 25 minutes into this. Quick question now. I have to move on now. That can we detect ammonium and heavy metals? The quick answer is we can. We do have a platform. We call it SenseltAll. We definitely can do ammonium and heavy metal. Question number 6 was somebody wants a 7 working electrode array. And so I just said to them, sure, we can take our Hypervalue electrodes. The way we make these Hypervalue electrodes, we make them in quite large sheets. So we can cut as many electrodes out as we want. So making 6, 7, 8 electrode arrays is really no problems. The only thing about 7 is it's a bit of a weird number. So many of our technologies are actually based around the idea of I say based around 6. There are 6 there. This meter that we've got coming will also take 6. So I would suggest that, if you're developing a multi-analyte, go for 6, especially if you want to work on a ZP platform. There was a question that came through as well. I realize this is a bit of a mini question. And will our Hypervalue electrodes work with the Sensit Smart Potentiostat? They will. And I actually had some really good feedback from PalmSense. They really like our Hypervalue electrodes because the Sensit Smart is quite a low power device, and when you plug it into a USB-C, it gets very little voltage from that USB-C. So they like our Hypervalue electrodes with the Sensit Smart because the counter electrode on our electrodes is silver chloride, and this really suits the compliance voltage output that the Sensit Smart is able to provide. So the quick answer is Hypervalue electrodes work really well with Sensit Smart, and Drop Sense actually quite like them. Question number 7 is a very specific question. Somebody wants to coat electrodes using some of the solutions. We generally never use more than 1 microliter. I think that's one of the problems. I've in the past told people to do 3 drops of 1 microliters, which is 3 microliters. But I actually come on one of our workshops because there we are pipetting onto working electrodes, and we're using something like a third of a microliter, and we're doing 3 drops in a row. So the question is, can you coat an electrode with less than 1 microliter? The quick answer is you can. You do have to be quite skilled, and the workshops are probably a good place to actually find that out. Question number 8, completely nothing to do with biosensors, just a general electrochemistry question. Somebody's doing they're adding ammonia and they're off-gassing hydrogen. They just wanted to know what potentiostats to use on this. You can't use things like PalmSense. These things are too low powered. You have to go for a manufacturer like Zana. We do distribute Zana in the UK and in Norway, but you have to use these high power potentiostats. And they do like a PP212, PP222, and a PP242. And all the numbers really mean are greater power requirements. So the larger your cell and the higher your currents and the greater the voltages you want to apply, then the more, let's say, the higher model you require. But if you keep everything fairly low power, then you can use a PP212. A couple of useful links as well, and I'll put those under the videos as well. Question number 9. Somebody wants to get hold of one of these, which is a sort of hypervalue electrode in a well. I don't know why we don't use at ZP. We don't use this more often. It's actually quite useful. So it sits in that little well, but they just want to know, well, what's covered up. So what's covered up is the working electrode is mostly untouched. The reference electrode, which is the guy that wraps around the edges, is covered up a bit. It doesn't matter because you really don't need much reference electrode in most electrochemical assays. It's funny actually because we do cover up the counter electrode, but the reason that we get away with it is because our counter electrode is silver chloride. So people think that you need a large counter electrode versus working electrode. It's really only true if your counter electrode is, for example, platinum. You don't know what the platinum electrode is really doing, but we do. It's doing a silver chloride oxidation or reduction, depending. And therefore, you don't need much counter in order to keep up with what's going on in the working. So, but what they're wondering is, because I think they're having a problem where they're trying to pipette onto the working electrode, but it's actually getting away from them and getting onto the other electrodes. I would actually ask them, if you pipette less than 1 microliter little droplets along here, you just don't have enough liquid to actually get off the working electrode. It's just not going to go. And that's how we do it. If you're really, really, really stuck, honestly, come to a workshop, because we can get more than 10 people in a room to do this pipetting, and it works pretty well. So please. Somebody's asking about CBD and THC analysis. So we have put some information out there in the past that, there was definitely a boom in hemp growing and CBD oil production, and we can test that stuff on our SenseltAll actual platform. Now, what we would do is watch some of our chili videos, because what you'll see is that we will take something like a chili sauce and we will actually end up diluting it in a buffer. And so the quick answer is we don't really care whether it's in an oil or in an aqueous. We will control its pH by doing a quick dilution in a buffer, and that's how we will take care of a lot of variables. So the quick answer is don't care if it's an oil, don't care if it's a liquid. If it's an oil, you can see here I actually have a vortexer next to us that you'd have to do a sort of vortexing to make sure you extracted the CBD in, or the THC into the buffer, and then the buffer would get pipetted onto the SenseltAll platform, and we get that data quite effortlessly to the cloud. Question number 7. 11, I should say. So Zimmer & Peacock, we're an ISO 13485 contract developer, contract manufacturer, about 22 years experience in glucose monitoring, and at least 15 years personally in CGM, continuous glucose monitoring. So we have a lot of CGM technologies. Wire sensors, these are something you can actually, microneedles, sweat analysis, though in strictly speaking on that one we've done lactate, and also subcutaneous. I'll just put that in there. I just want to go back a little bit as well and say that wire CGM sensors can be bought actually off our website. Microneedles are available on our website. Non-invasive patches and glucose sensors are actually available on our website. Implanted sensors are also actually available on our website. So these are the standard products that we have. But don't just jump into these. These really, if you're a commercial organization, these have to be done in collaboration with us. It's not enough to just get hold of technology. Applications, data science, these, we really have to dig into this completely. But we do have a lot of microneedle technologies. These can be found on our websites. This is a gallery that we run. We're also really we're absolutely experts on the formulation of sensors. If you're having a conversation about glucose sensors, it's not enough to just talk about glucose sensor. You're talking about a generation 1 glucose sensor, a generation 2 glucose sensor, a generation 3 glucose sensor. If you're doing this in a commercial entity, you have to talk about IP, the ability, the freedom to operate. This is one of our sort of most complete sensor technologies. This is the sensor here, and there's an entire package back here which has the sensor, the transducer, and also power supply as well. So we've been a lot. Whoops, a daisy. This one, I know I've talked. Aftab is online today. He knows I've talked about this a lot. But slight side note: the Easy Flex that was shown earlier on. This is the kind of next generation of that. Actually, this is that much more accurate and precise board, I would say. But this CGM package gets implanted into fish, just for the interest as well. It's also got a cortisol version as well. And we do have an entire platform around helping people with accelerating the development of products around CGM. I've got a kind of a link down here, but we do have a lot of material on it. I mean, for commercial organizations, don't just jump into the products. You do have to, work with ZP, because you have to talk about, the IP landscape. There's a lot of people out there. You have to really have a kind of an IP discussion before you go anywhere with this. It's probably worth saying that at ZP, we are ISO 13485. We have what's called a Class 7 clean room. It does have Class 5 zones on it, and it's for what's called aseptic manufacturing. So we are manufacturing CGM sensors, both transdermal and implantable, in this facility. And I think this is the only contract facility that specializes in CGM in the world. So we do have a uniqueness in the ability not only to develop but also to manufacture glucose sensors as well. So you can work with us on micro projects, mini projects, and also what we call proof of concept projects as well. We've also had an inquiry coming in from Asia as well. Somebody wants 20 electrochemical sensing chips and a dozen meters. The solution for this is somebody comes to us and says, look, I need something to use in a sort of, I would call it a preclinical trial. Then, we do have our SenseltAll platform. It exists. The electrodes are already compatible with it. We have the ability to send all that data to the cloud, and we have that the ability to send that data in our clouds to another cloud using an API. If you're going to be developing a sensor for biomarker, the ZP electrodes are pretty good. You are going to have to, or commission ZP are going to have to functionalize them to make them specific to the biomarker of interest. So that's a variable that has to be talked about. The meters are not. The meters are something standard. The apps are standard. The method file. So the method, so if a new sensor is developed, there's two new developments. There's the sensor itself, and there's the method file. Is it voltammetry? Is it amperometry? That has to be developed. We would do this, by the way, as a proof of concept study. Proof of concept from Zimmer Peacock is generally 22,000 euros and about 111 hours. So if it's a new kidney biomarker or new marker for kidney diseases, etc., then it needs functionalization and it needs a method file. Once those two things exist, we can actually just plug it into our platform, and our platform will essentially take care of the rest. The API is important because, we believe that we have to support other entrepreneurs, and other entrepreneurs need access to the data, and they get access to the data then using an API call on Julie. Julie's a database that exists. It's got an API function on it. You can look at all these APIs and you can call across data from it. So this person's going to need our Spectrum sensors, and our SenseltAll platform are the things they really need. If they want to develop the sensors themselves, that's fine. If they want ZP to do it, we would do it as a proof of concept. Question number 13. We have lots of ways of working with people. I've got a couple of videos playing here because really the two big areas we work in are often wearables or continuous monitoring, or IVD or discrete monitoring, in vitro diagnostics. So we do have troponin sensors, cortisol sensors, lactate sensors. I have looked at epinephrine in the past. I'm pretty sure we can do epinephrine. And also bacterial sensors and fungi sensors. We have worked on these. I mean, bacteria, I'm a bit more familiar with it. You can do it. There's lots of ways of doing bacteria. You can do it by DNA, which is harder. You can also do it by antibody, which can be very specific, and sometimes people want non-specific signals. So it's not, bacteria and fungi are sort of the more challenging things. The molecules are a lot easier. And as I say, we've got two form factors, IVD and wearable form factors. And it's probably worth, so I just want to sort of dive into it a little bit deeper. We have all these kind of configurations. But these configurations for wearables, non-invasive, minimally invasive, invasive, implanted. We do have we have sensors, we have a board. We have already integrated this board ourselves with a module called the ESP32, which is great because then it gives out a Bluetooth signal. So our sensors, in order to make like a troponin ice sensing system, you need the sensor, you need the single purpose electronics, which we do have, and then actually we have done that piece of engineering to actually plug it into some of these off-the-shelf items like an ESP32, because then it does give us Bluetooth and sometimes Wi-Fi as well. So we're quite familiar with that. The thing is, to work with ZP on some of these tougher challenges, it has to be a micro project, a mini project, or a proof of concept, just to get going. Micro projects really more about planning. Mini project allows a bit of planning and some engineering and proof of concept. We can generally get, I want to say, TRL3 kind of level with a proof of concept study. So questions. There was a lot of questions this week. So at ZP, we're very used to developing IVDs. No issues. Cell culturing, we do have a lot of biosensors, glucose, lactate, oxygen, pH, conductivity. These are all pretty useful for cell culturing, but for that one, we do it as a product as a service. So we really have to engage on some sort of project with it. Cortisol sensing. I want to really congratulate the person for reaching out to us. I'm not able to provide a sensor at this point, but I really do wish them great luck on that, especially because of the young age, so thank you. Data from glucose sensing. Your data makes sense in the way that you're actually doing the sensing. A couple of things. Watch that video featuring Andre, and also you have to be testing in the clinical range. And I must admit that Easy Flex board that you're using, we've always tested it in the kind of 0 to 20 millimolar range. So you're going, I think almost, was it 0.2 millimolar, but at least an order of magnitude less. So I'm a little bit hesitant on that, actually, on that particular, not on that board, not on the sensor, by the way. Sensor I don't have no problems with. Ammonium sensors, we have ammonium sensors. If people want to have lots of working electrodes, the Hypervalue platform will do it. It's just the way we cut them out, no big issues. Biosensor fabrication, you can generally, we would put down 1 microliter of solution in about 3 drops though, so that's almost a third each. And people can pipette this stuff. We definitely have them at the workshops doing that. Fuel cell application, you need those Zana potentiostats. Hypervalue electrode in the well. The working electrode's not covered up, and I think that well is not going to stop you spilling off the working electrode. I think you have to reduce the volume to stop spilling off the working electrode. CBD detection and THC. It's the SenseltAll platform, following some of the protocols that you'll see in our food sense box. CGM discussions. Zimmer Peacock is a very experienced contract developer, contract manufacturer of CGMs. We work on transdermal sensors, microneedles, patch sensors, implantable sensors. We have both rapid development and the manufacturing capability. It very clearly says in our ISO 13485 that we are certified for that work. IVD development and electrodes, and then lastly, things like those troponin I, those lactates type sensors. Yeah, we've got the parts, but it needs to be done as part of a project. So I want to say thank you very much. I'm so sorry for going on so long today, but there were a lot of questions, and I essentially want to wish people a good week. We're coming up to the Christmas break. I realize, but don't worry, these webinars will continue. Though I'm not sure how many questions I'll really get over the vacation period, but just take care and have a good time. Well, have a happy vacation if you're taking vacation soon. Okay, thanks very much. It's appreciated.